Hello everyone. Welcome to this session on the regional probabilistic climate risk assessment. Let me now introduce our first speaker, David Huard from Uranus, who will talk about estimating the likelihood of greenhouse gas concentration scenarios from probabilistic integrated assessment model simulation. So at the end of each presentation, if you have questions, just leave it through the chat or raise your hand. So I will moderate the first part and David will moderate the second part. So David, I will let you share your screen.
Excellent. Are you able to admit people in the room while I'm speaking?
Yeah, I can. I'm doing that job.
Excellent. Thank you. So are you able to see my screen? Yep.
Yep.
Excellent. So the point of this talk is to discuss how we can estimate the likelihood of different greenhouse gas concentration scenarios that we typically use in climate risk assessments. And the idea is that there's a missing ingredient, I believe, in future climate risk analysis. And when we look at the definition of risk, it's basically the probability of a hazard times the cost of this hazard. And to estimate the probability of a future climate hazard, what we have at this moment is this kind of workflow. We have concentration pathways, so our scenarios that feed into multi-model experiments from CMIP, for example. And then each GCM in those experiments runs different realizations, which yield time series that we can analyze to extract hazards and build the kind of distributions of those hazards. And so in terms of probabilities, what we have on the right is a parametric uncertainty related to the fit of the distribution for those hazards. In terms of the simulation ensembles, we have an aleatoric uncertainty due to natural variability. From the climate models, we have an epistemic uncertainty because we don't fully understand all climate processes. But on the left, we don't really have probabilities for the storylines that drive those models. So if we want a probabilistic assessments of the hazards and risk, we need to be able to assign probabilities to those concentration pathways on the left. And so those concentrations, where are they coming from? They're coming from a reduced complexity model called MAGIC, which is able to convert greenhouse gas emissions into concentrations. And these greenhouse gas emissions that are defined in the RCP and SSP scenarios, they themselves come from integrated assessment models, which are themselves based on socioeconomic hypotheses. And so, for example, in RCP and CMIP5, the RCPs 2.6, 4.5, 6.0, and 8.5 come from different integrated assessment models, image, GCAM, AIM, and message, which basically describe different pathways for emissions. And these emissions go through the MAGIC model to create concentrations, which are then fed to GCMs. And so the CMIP5 experimental design looks like this, where we have these integrated assessment models on the left. They generate emissions, then MAGIC models the carbon cycle processes, which allows it to define greenhouse gas concentrations, which basically are prescribed to global climate models. And so these greenhouse gas concentrations are the boundary conditions for CMIP5 experiments. Note that there is one experiment called ESM RCP 8.5, which is fed directly from greenhouse gas emissions. So it's an emission-driven experiment. And to run that, you need Earth system models that are able to, will have a full carbon cycle processes defined. So my objective here is to assign probabilities to these greenhouse gas concentration scenarios that we find in this figure. And just to be clear, I don't want to assign probabilities to greenhouse gas emissions because there's this magic 6 model in between, and we know it has biases and it's a reduced form, well, a reduced complexity model. And so I don't entirely trust it to provide the correct concentrations and account for all the uncertainties in this in carbon cycle processes. So basically what I want are probabilities for these greenhouse gas concentrations. And the way I propose we do that is by using probabilistic simulations from integrated assessment models. So I've shown you the assessment models that were used for RCP, for the RCPs in CMIP 5, but there are other integrated assessment models, and some of them shown here provide probabilistic ensembles. So basically what they're doing is that they sample parameters within the model, so the uncertain parameters, and from those sampled parameters generate different emission trajectories. And so what you see is the spread of all those different emission trajectories. And you can say that if you've chosen the parameter distributions correctly, so describing your own uncertainties about the parameters, what you get is a kind of probabilistic assessment of future emissions. And what I propose we do is that we use those probabilistic emissions to assign probabilities to the concentration pathways used in RCPs and SSPs. And to do that, we need to backtrack basically from the concentrations that are prescribed to GCM to emissions that I can compare to those probabilistic emissions from integrated assessment models. And the way we can do that, if you look on the right of this figure, is that we have time series of atmospheric concentrations for carbon dioxide, which is prescribed to GCMs by the CMIP experimental design. And then within the GCMs themselves, we have ocean fluxes and land fluxes. And it's basically a budget. So if you compute at each year these fluxes from the atmosphere into the ocean and into the land, and you compute the difference between each year in the atmospheric concentration, which is prescribed by the experimental design, then any imbalance between those differences in concentrations and these fluxes has to come from fossil fuel emissions. So basically, by doing a simple budget, you can diagnose or backtrack the compatible emissions or the fossil fuel emissions that are compatible with the prescribed concentrations. And this work has been done by Jones for CMIP 5 and by Liddicoat for CMIP 6. And I'm basically doing what they did to create an ensemble of compatible emissions. And these are the results. So on the left for CMIP 5 and on the right for CMIP 6, you get what emissions are compatible with the prescribed concentrations. And so the spread in the multimodal ensemble for each scenario, each experiment, each scenario, is basically due to differences in the carbon cycle processes within each GCM. And I don't want to spend too much time on this, unless to say that there are differences across models and differences between the emissions that are part of the scenario and the emissions that we diagnose from GCM models. And so this is partly due to differences in the carbon cycle processes between MAGIC and these GCMs. Now, if I fit a normal distribution for each year on those multimodal simulations, what I get is this. Also note that instead of annual emissions here, I'm computing cumulative emissions, so from the 18th century on. And so now for each year, I have a normal distribution. So the mean is the thick line and the envelope is the standard deviation around the mean. And this defines basically a likelihood for emissions for each scenario. So I can then use that to basically compute the likelihood for the scenarios. And just, I don't want to go too much into the details here of the formulas, but I'm using Bayesian analysis. And what I'm essentially doing is computing the overlap between the probabilistic emissions that whose histogram I'm showing in gray here, and the likelihood defined by the normal distribution fitted to the diagnosed compatible emissions for each scenario, which I've shown in colored thick lines here. So basically, if I have a strong overlap between here SSP2 4.5 and the probabilistic emissions in gray. That means that this scenario is more likely, at least according to these probabilistic emission scenarios. And so I can do that for every year and every probabilistic IAM. And what I get is the following. So these are the main results. On the top row, you've got results for CMIP5 and the 4 RCPs, and on the bottom row for CMIP6 and the 4 Tier 1 SSPs. And basically the columns are the results for each different integrated assessment model that provides probabilistic emissions. And when we look at the results, we see that RCP 8.5, for example, is fairly likely for Fike and Matthews integrated assessment models, but for most of the others, it's fairly unlikely. So after 2050, it goes quickly down to almost 0. And so what that tells us is that RCP is fairly, is likely until the middle of the century, but then becomes more and more likely as we go to the end of the century. If we look at CMIP6, we see that for most probabilistic integrated assessment models, SSP 2.4.5 is fairly likely, along with SSP 1 2.6. And that's kind of fairly different from the results that we got in CMIP5, where RCP 2.6 was fairly unlikely. And so the idea is that, well, I'm not saying we should use those results because we only have 5 different integrated assessment models. They were certainly not meant to be used in this way. They make no claim of being predictive, but I think it shows that there is potential to use such integrated assessment models and probabilistic emissions from them to assign weights to the different scenarios. And so again, I'm not saying we should use those results. It's not decision yet ready. It's only based on 5 probabilistic emission ensembles. Also, because the experiments in CMIP are concentration driven, the effect of carbon cycle feedbacks is damped. So we don't have the full, I'd say, description of what emissions imply for future climate change. Also, because the ensemble size in the CMIP experiments are not even, we've got some artificial differences in the likelihoods computed that could be fixed, but it's it's another layer of analysis. And as I said, the integrated assessment models that I use were not meant to be predictive. So it's kind of a work in progress, I suppose. But the hope is that eventually we'll have probabilistic emissions with an epistemic definition of uncertainty that feed into multimodal experiments. And then we'd have a full chain where we can analyze uncertainties and assess the risk of future climate hazards. And that's it. I'm ready to take any questions.
Thank you, David. So we had a question from Connor Anderson. You are muted.
Oh, sorry. I was just saying. I thought I had pressed the applause button. Sorry.
Okay. Adam Monahan.
Hi, David. Thanks for the presentation. Just a question about the assignment of probabilities to the different emission scenarios. The emission scenarios are meant to be taken as extended scenarios over a period of time, whereas you're assigning probabilities separately at each year. So would another approach be to actually assign overall probabilities to the entire scenario trajectory rather than having these time-dependent probabilities, which would, essentially are almost imagine switching between trajectories as you move along through time?
That's an excellent question, and I've kind of grappled with it. That certainly could be done, and the question is, I think, one of interpretation. How far? How dependent are hazards on past emissions, essentially on the pathway to get there? versus like instantaneous emissions or cumulative emissions. And I've chosen like that approach of having of conditioning on cumulative emissions, but I'm open to the idea of using like the full scenario probability. But it would kind of be weird because if you looked at let's say hazards in 2050, you'd have to stop in 2050 to avoid assigning probabilities based on what happens afterwards, because that would make no sense. And so I think like cumulative emissions provide that kind of compromise between accounting for what went on in the past without assigning probabilities based on what's going to happen in the future.
Okay, thanks.
Okay, any other question for David?
My time is up anyway, Martin, so thanks.
Perfect, thank you, David. Okay, so our next talk would be Gerry from Environment Canada. So I'll let you share your screen. Who will present which scenario should I use? So the stage is to you, Gerry.
Thanks, conveners, Martin, David. Thanks everyone too for showing up Friday near the end, especially out east. So this is a talk that really follows on closely from the talk we just had. And indeed, we've been working sort of together on this theme for a little while now because we think it's important. So I'll share some work that we're pushing forward myself, as well as colleagues Neil Swart and David, really to tackle this really vexing question that we as climate service providers almost unanimously get in the course of trying to help users develop climate impact risk and adaptation thinking, which is the question, which scenario should I use? Almost every project ends up with a conversation around this question. And what I'll try and show here is one sort of deep dive into some into approach that we're taking to actually try and actually circumvent this question entirely by using ensembles of energy emission and Earth system models to actually try and provide a quantification of sorts of emission uncertainty. Again, specifically for the purpose of on the ground, regional, municipal scale, indeed, climate impact risk assessments, which are the underpinnings of climate adaptation thinking and climate adaptation in general. So I'll try and frame the problem out as best as I can with this schematic. And the problem in a nutshell to me is that the uncertainty, but the quantitative uncertainty budget, so to speak, of future climate change is not yet closed. I think that's one way to put it. And we can think about that by looking at this schematic. And so we have here some measure of a climate parameter, let's say temperature, at some location XY on the surface of the Earth at some time in the future. And we don't know the exact value of this parameter for a few important reasons. Number one is just aleatoric, natural, irreducible, internal variability, uncertainty. And this is just to say the climate system, the physical climate system is noisy and chaotic, technically so. And so we can't pin that down to an exact number, especially far out into the future, but we can quantify that uncertainty and we can analyze it. And we can do that with tools like single model initial condition large ensembles. All right, there's another dimension of uncertainty, which is epistemic model uncertainty, which is sort of to say our understanding of the geophysical system is never perfect, nor is our representation of that system in these climate and Earth system models that we send forward in time, right? And so that uncertainty is epistemic, which means we have some control over that. As our knowledge improves, we can change that bound of uncertainty, and we can also analyze that quantitatively using things like multi-model ensembles, like the coupled model intercomparison project, right? Now, these two tools are being combined together relatively recently into so-called multi-model large ensembles, very big, massive data sets that are very powerful nonetheless, because they allow these two dimensions of uncertainty to be analyzed in some sense together, right? And so we start to combine an analysis of uncertainty, not just for one, but multiple dimensions of overall climate uncertainty. But that doesn't answer the question or doesn't solve the problem, because the last dimension of climate uncertainty, that related to our actions in the future, specifically around emissions, is really explicitly unquantified right now. And it's explicitly unquantified because explorations of future emissions today, like unanimously, essentially take the form of scenarios, which are narrative, storyline driven, sort of what if explorations of future emissions. And you can find language that states this explicitly in pretty much all IPCC reports, including IPCC AR6. And you can read this quote. It explicitly says that this dimension of uncertainty is not pinned down in a quantitative sense. It uses scenarios. And so this is the area that we're trying to tackle here, to close, if you want to say close, the uncertainty budget around future climate uncertainty. Now, this is not a new conversation, and we're not new to the conversation. We're new to the conversation, which has been going on for kind of, as far as we can tell, 20 years or so, with the first development of scenario approaches, and probably even before that, I'm sure. And you can find a rich literature of this debate between, on one hand, the need for probabilistic emission projections, and on the other hand, some philosophical arguments why those might arguably not be possible. And so we'll take one side of the argument here, as you'll see moving forward. So what I'll describe now is the word innovation. Sorry, I made these slides for another workshop, and they asked specifically to include what the innovation was. So I don't want to sound pompous when I say innovation. It's sort of built into the slides here. But what we'll demonstrate is an approach to combine CEPM, which is sort of a reduced form energy emissions model, with actual Earth system modeling to try and quantify emission uncertainty. And I'll describe how that happens next. So we start with the core of the CEPM model, which it is premised around, in fact, an ordinary differential equation describing the rate of change of the geological carbon reserve. So it's very much a sort of geophysically centered model, if you want to say that. There's factors endogenous to the model. I'm going to borrow some language from integrated assessment modeling. The model calculates internally things like fossil resource depletion, global energy demand, and percent of global energy supplied by fossil fuels versus non-fossil fuels. And a key output of this model is carbon emissions as CO2. That's a caveat that we'll come back to at the end. Now, there's exogenous variables. I'm going to borrow some more terminology from integrated assessment modeling, things that we feed into the model to make it run, boundary conditions, things like carbon pricing, non-fossil energy pricing, population growth, per capita energy consumption, like these. These are prescribed to the model, and the model runs and produces carbon emissions, essentially. Now, these exogenous variables, these forcing factors, we can feed many values for these into the model and run the model many times in large ensemble mode, and develop from distributions of inputs, distributions of outputs of carbon emissions. Now, you've seen plots of this already in the previous talk, and you'll see some of these plots again here. So this is from one of those four models that you heard about previously. This is the CEPM contribution. Now, here's a plot of that cloud of model results in gray. And superimposed on those are the RCPs, which I believe are the solid, and the SSPs, which are the dashed lines. And so one observation to make, an eyeball norm, is that CEPM, qualitatively reproduces really well the characteristics of the RCP and SSP CO2, carbon as CO2 emissions trajectories from essentially now out to year 2100. Now, it doesn't do some things. It does do negative emissions, so it bottoms out at essentially zero, whereas the 2.6s go below because that's another story. But in a qualitative sense, the model is capturing the nature of what the RCPs and SSPs portray using their storyline-driven approaches. Now, we would argue, though, that because the model is driven by sort of a controlled set of inputs, and it's also a controlled single model, we can start to think, and Adam, hold your questions. You made a good point. We can start to think about quantizing the model results on some sense in a year-by-year basis. And this is where we start to step away from the scenario-based approach. We can quantize these by percentile, develop some sense of a composite emission projections. And I'm starting to use the word projection here very consciously instead of scenarios. What we get when we do that is a picture that looks like this, developed from that large ensemble of CPM simulations, 100,000 of them. Now, these are identical in technical form and function to SSP or RCP emission scenarios you can go and download and run Earth system models with, which are carbon cycle enabled models like we heard from David. Now, this is what we've done. We've taken these emission scenarios, composite percentile based emission scenarios, which have ingrained in them, we would argue, some sense of emission likelihood, and driven an ensemble of CAN-ESM5 ESM models with each of these fifth percentile ranked emission projections. We've swathed out as best as we could some internal variability space. So for each of these 5th percentile levels, we've done 3, essentially a mini SMILE per percentile level of emissions. And out of that, in this demonstration, we've pushed out, we get 57 global physical climate change projections, totally like what you would see if you went and downloaded stuff from CMIP6 archive. In fact, this is thanks to Neil. I'm not sure if he's on the call here, but you would navigate this just like you would the CMIP6 data set. So our last step of this exploration is to actually try and pilot out what a regional impact and risk assessment would look like if it was fed with this kind of information that came with not just projections of physical variables, but also some metadata essentially describing, in some sense, how likely one level of change is versus another for a particular point in time. And so we'll end with sort of an exploration of this new hypothetical impact assessment with this kind of information. Near and dear to our hearts, for some of us, we lived through it, was the Western North America extreme heat wave of 2021. So we'll take this as a case study to play with. Here's a picture of that. I'm sure many people here are experts on this, and no need to repeat. Here's some common images. Lives were lost, communities were lost. And this is driving to now open calls for municipalities to develop extreme heat risk mapping, and how events like this are going to change in likelihood in the future. And this is exactly the kind of on-the-ground project that motivated us to bring this whole kind of project along. This is the kind of effort that probabilistic information would be really well suited to support, we argue. Now, what do you get when you slice BC and Alberta out of CANI SM5 results? We didn't downscale our bias correct. Interest of scope. We get plots like this when we bring in not just the information itself, but metadata describing emissions probability. With this information, you can start to explore climate change, we argue, in a really powerful and actionable way. So we can explore changes to some metric of extreme heat, in this case, heat wave maximum length, units of days, not just in time, the x-axis, but also across the y-axis here, which is emission scenario probability of exceedance. You can borrow language from return period approaches now. If you slice this type of Hofmuller plot vertically, let's take at the end of the century, we can start to develop what, at least on the face of it, sound like very powerful statements, which would be really welcome by on the ground people trying to develop climate change risk work and adaptation responses. We can develop statements arguably like this. Given our current knowledge and models, average maximum heat wave length is extremely likely to exceed 4 days, but extremely unlikely to exceed 14 days by the end of the century. Now, don't hang your hat on these numbers. This is not meant to be fed into any real projects here, but the point of the statement is the important thing. What's maybe most important is what's missing. This statement is not conditioned at all on any scenario. Emission uncertainty is explicitly folded into this statement through calibrated likelihood language. Extremely likely and extremely unlikely come from calibrated IPCC AR6 likelihood language, right? We don't need to provide now users with scenarios. It's built into the statement. Other calibrated language here is the first phrase, given our current knowledge and models. We have some vague sense that this is sort of, you can reflect changes to these estimates in some sort of Bayesian way. You can start to learn and evolve this uncertainty, just like we evolve uncertainty in epistemic model uncertainty, geophysical climate model uncertainty. Now, aspirationally, we can come back to our multi-model large ensembles and think that maybe if this approach can be studied and nailed down and no fatal flaws are found, then we can start to think about bringing that last dimension of uncertainty, epistemic emission uncertainty, into these multi-model large ensembles and really close evaluations of the full range of climate uncertainty across each of these 3 dimensions. We have challenges. There's philosophical and technical challenges. In the interest of time, I won't run over them, but I'm sure many people here already are having flags raised, and so welcome that. We would look to CMIP7 quite aspirationally as a place where, in addition to scenario-based projections, we can start to think maybe about providing really adaptation-focused, probabilistic emission projections that work we think, much better in the on-the-ground adaptation sense. And with that, thanks a lot for your time.
Thank you, Jeremy. We have time maybe for one question. I don't see any for now. Oh, yeah. Karen Smith.
Sure, thanks. Hi, Jeremy. That was really, really interesting. I just have a question about, in practice, you said that you always get this question, which scenario should I use? And I guess I'm wondering, to what extent, basing kind of impact assessment on something like warming levels, like global warming levels versus, different scenarios is ever something that's considered in practice, or whether it's always kind of thinking about temporal evolution and things as impacts as a function of time.
Warming levels is one great way to circumvent some of the scenario difficulties. I think one difficulty with levels of global warming, which doesn't preclude its use completely, I would say, is that some things in the real world are just based on time, deterioration of infrastructure, strategic plans around investments, asset management. And so sometimes you still run into the question of time, even when you go to warming levels. So it's definitely one avenue to do it, and certainly one avenue to consider too. Yeah.
Okay, thank you, Jeremy. So now we'll pass to our next speaker. I will let David present the next speaker. So there were other questions in the chat. So Jeremy, you could go have a look there.
Hi everyone. Is it clear? Anything good?
Yep. Please go ahead.
Okay. Thank you. Hello. Yeah. My name is Yong Xiaoliang. I'm a third-year PhD coming from Munich. So happy to present my work here. The topic here focus on the observationally constrained predictions of regional warming. So first of all, I acknowledge my supervisor's contribution to this work. So motivation of this study, people concern the warming predictions over regions. Here provide you results, then applying the multimodal projections from the CMOS, which is couple model intercomparison project phase 6. The x-axis in the panel plot is the year, the y-axis is the predictions. The red shading is the uncertainty range from multimodals. The dotted line is the best estimate. The vertical bar shows the last 20 years of the century projections, which is uncertainty range. The corresponding quantity of the end of the century of the last 20 years show the lower positions of the member. We here provide two regions, two Canadian regions. One is the Western Canada, another is the Eastern Canada. You can refer the map in the lower position here. So from this number for the last 20 years projections, so we can see the uncertainty is quite large for both regions, which the uncertainty range can reach to more than 7 Kelvin. So this result is based on the SSP 5 8.5 scenario, which is a high emissions designed to the CMOS 6 and with reference period 1995 to 2014. So it provides so large uncertainty range for the community who concern, the specific warming targets to make policy to the climate adaptation. So it may not provide accurate or the reliable results considered so large uncertainty range. And the newly published IPCC-R6 report do apply a technique called observational constraint to narrow down the global warming. But this robust technique have not applied for the regional warming predictions. The AR6 report use unconstrained model estimate for the regional warming predictions. So here we are thinking, could we use such a robust method to narrow down the uncertainty range in the regional warming predictions? because previous study do not have apply this method to. We do not have good knowledge for the performance of the technique on the regional scale. So first, we want to evaluate the performance of the technique over the regions we concern, and we expect applying this technique can substantially narrow down the uncertainty range compared with the unconstrained projections for the 24th century warming method. So for the method called the observational constraint, so this method rely on the stable emerging relationship between historical metric and the projected variable. For the projected variable here is the regional warming. So as shown in this symmetrical plot, if we have the historical metric, then can better explain the projected variable. So then we can get a tight emergent relationship. So this emergent relationship should rely on the solid physical explanations for this model difference to explain this regional warming difference. So the dots here represent the different climate models. When we get this solid emergent relationship and then introduce the observed quantities of the historical metric into this framework, can get a constraint uncertainty for the future projections. We're showing this green shading compared with unconstrained, the unconstrained from the full model range, uncertainty range. So we expect that the constraint projection could substantially narrow down the uncertainty range. So the first important thing is to find out the metric have a clear physical basis to explain the model difference of the projected warming. Previous study do tell us that for the CMF6 or CMF5, the model difference of the projected warming can be well explained by the cloud physics, which models have there's a significant model difference of the cloud feedbacks. So we call this cloud metric as a global metric because pre-study used those metrics to try to constrain the global mean warming or the climate models, the model's climate sensitivity, because there is connections between the regional warming and the global warming for the individual models. So my study also expect applying those global metric, which I called it the cloud metrics, can also work for the regional constraint. So, but previous study do design lots of the cloud metric up to 20. My study do not use all of them following my recent study. So there are just the two metric, and BRC and BCS are selected because they are more independent and have the clear physical basis of those cloud feedbacks. In addition to the global metric, we also consider the regional metrics. So because the regional metrics involve the information of the regional, models have the model, there's a model difference of the regional warming. So that's involve those regional metric can provide additional information in addition to the global metrics. This something pre-study usually do then, like apply the regional metric to constrain the regional warming in the future. So we expect involving those metric can still get a more robust emerging relationship comparing apply the global metric alone. So my study measure those regional metric by the trend climatology and variability. So the regional climate index showing the red table here, not apply all of them, use a metric selection process to just apply the subset of the metric because some of metrics share the similar information, which will increase the redundancy of our observational constraint framework. So we have two choice of metric. One is use the global metric alone, another is involving the regional metrics in addition to the global metric. So which perform best? We do not have observations in the future. So to evaluate the performance, applying the different choice of metrics to do the constraint projections. So we can use the models to survey pseudo-variations, saying each model to survey pseudo-variations in term and use the rest of model to predict the pseudo-variations. So when predict the pseudo-variations, you can apply the different choice of metric and compare the results with these constraint predictions, compare the result between the constraint prediction using those metrics with the pseudo-variation to see which choice is the best. So we value three aspects. One is accuracy, second is effectiveness and reliability. For the accuracy, we want to know how much the distance between the constraint values to the pseudo-variations measured by the correlation coefficient and reduction of RMSE between the constraint projected means value and pseudo-variations. Also value the effectiveness, because we do expect applying this technique with the metric select can get a narrow uncertainty range compared with unconstrained. So here measure the weights of the constraint uncertainty. And also value the reliability, which because we have a uncertainty estimate based on the metric chosen. So we want to know whether the estimate of uncertainty is reliable, saying to test if the pseudo-variations can lie in the constraint 5 to 95 uncertainty range. So there are three major focus here for the evaluation process. Because we choose the metric from CMAP6, if just apply this test using the CMAP6 median ensembles, that is a purely ensemble test. So in addition to this, we consider the out-of-sample test like to choose metric in CMAP6, but evaluate the performance by CMAP5 to see whether there's a stable performance from in-sample test to out-of-sample test. So if there are some changes, that will suggest the overfitting of involving some metric chosen. Regarding the time, I will only go through the details of accuracy. We evaluate. So here show the x-axis here show the different regions, and the regions in the green box is the Canadian regions. If just apply the global metrics showing the green bar, they apply involving the regional metrics showing the blank bar. So this performance measured by the correlation coefficient and reduction in the RMSE, we expect there is a greater and positive value of correlation coefficient and a greater value of reduction in RMSE. And the spread of the bar here represent the impact of internal variability. So we can see for compare the green and blue and the blank bar. So we see that the involving the regional constraint do increase the do show the regional constraint, regional metric are sensitive to the internal variability, which show a higher spread for most regions here. But global metric perform generally vary across different regions from in-sample test to out-of-sample test. If we focus on the blank bar, which just the cases of involving the regional metric in addition to global metric, we see that the out-of-sample test do show a decreased performance. When in sample test it perform generally is perform not too bad, but for the out of sample test we see the performance decrease. This show clear evidence of overfitting when involving this regional metric. But for the global metric to constrain the regional warming, it's perform robust, not sensitive to the internal variability, and also there is a stable performance from these two tests. Regarding the time, not to introduce the effectiveness and the reliability, but for the other two aspects also show the global metric alone perform the best. limit impact of internal variability and do not show overfittings compared with involving the regional constraint. So yeah, so the evaluation suggests that the global metrics perform the best. So applying the global metric to do the observational constraint, showing the green shading here compared with unconstrained showing red. For the two Canadian regions, we can see observational constraint do substantially reduce the uncertainty range. So the bar here shows the last 20 years projections, and the corresponding quantity showing this lower position compared with unconstrained. We calculate the reduction percentage, which for both regions can more than 35% of the reductions if applying the global metric to do the observational constraint. Also do the similar operations on the SAP 2.6, get the similar reduction percentage. The SAP 2.6 is a lower emission scenario, which consistent with the Paris Agreement target. So summary, I think regarding the time, we'll go through the details. Yeah, so, but I will stop here to happy to take your questions and comments. Thank you. Yeah.
Yep. Thank you. So anyone has a question? Otherwise, I have one. Are you basically selecting models that agree with each other?
Select model with each other, you mean?
Well, in your sampling test, you're comparing one model against the other models and finding those that agree with each other. Did I understand correctly?
Well, I think the method here is based on this linear relationship between the historical metric and the projections, not compare models with each other. Is when there is emergent relationship built up, then introduce the observations to infer the constraint projection.
But I understood that you had pseudo observations and not real world observations.
Oh, you mean the evaluation?
Yeah.
Yeah, so then pick up each model to serve as observation and use the rest of models to predict these observations.
And so isn't that an assessment of agreement among models?
Agreement of agreement. I may not measure this agreement. I just see whether these predictions, the rest of models' predictions are close to those to the pseudo observations.
Okay. Well, thanks a lot for the presentation. And Martin, you're next. All good? Please unmute.
Okay. Good?
All good.
Sorry for that. Okay, hello everyone. So I changed a bit the title of my presentation because I would like to focus more here on the way to get to constraint on projection. So like how the calculation of regional weight is affected by different factors such as internal variability and the selection of the evaluation matrix for the models. So a bit of context, constraining ensembles of climate change projections aims to increase our confidence and so reduce uncertainty. Recently, the IPCC used multiple lines of evidence to constrain the estimate of the global sensitivity. But at the regional scale, the benefits of weighting projections are often hindered by the amount of observation, internal variability, and the selection of model evaluation metrics. So the objectives here are really to assess the impact of selecting and combining some performance metrics associated with the regional projection, and to evaluate also to quantify the uncertainty due to the internal variability in the calculation of weights. So for that, we will use an equation that is widely used in the emergent constraint literature. So it's basically a normal distribution function that is function of the bias of the models with difference with observation. And here the sigma is simply scaling this difference. So it's the standard deviation of that difference, which we estimate in this project using a large SMILE ensemble, so containing many members from different initial conditions. What is interesting with this equation is that we can interpret the bias as a generalized distance. So you can decompose it into several directions. So you can combine, for instance, a bias across different variables or seasons, for example. And after that, like the total weight of your model will be simply a multiplication of the different individual weights associated with this particular model. So for that, we will use an heterogeneous ensemble of climate projections. So here we have a 180 simulation from historical and 2 RCPs. So and it contains GCM models, Cordex regional climate models, and on the bottom right, you see the Climax single model initial large ensemble, which contains 50 runs from CANI-SM2 that were downscaled using the Canadian Regional Climate Model version 5 at 0.11 degrees of resolution. So if we go look a bit more detail, you see.
Martin, you muted yourself.
David, you should be able to unmute him.
Well, he's not muted on.
Oh, I see.
On my console, so I assume it's on his end.
Right.
You are unmuted from my side.
Oh, Martin, we still can't hear you.
Yes, some headphones have an integrated mute button on the cable.
Now, do you hear me?
Yes. Please go ahead.
Sorry for that. Okay, so I'll skip that part. So you see many members of GCM which were downscaled by regional models. So at the end, you can have either regional model projections or data directly from the GCM.
Martin, can you please share your screen?
Yeah, thank you. Okay, you see and you hear me?
Yes.
Okay, sorry. So we'll use the result extracted over the southern Quebec region and calculate the weight for seasonal means and historical trends and compare with the observations. So we have on the left the bias of the different model simulations. So for the first column is the large ensemble containing 50 members. After that, you have Cordex regional models and CMIP5. So you see that the difference between models and the observation, the impact of internal variability is much smaller than difference between the different models. So if we compute the weights for each simulation, here they are classified for each model if there are several members. So they are in the same column. And on the vertical axis, you have the value of the weight. So we can see here there, these can be very small value because we have a logarithmic scale and an exponential function, so it can be very small. But it's useful to visualize those results. So the lowest is the point, the largest is the bias of that model. So we can see that few models dominate in the weight. You can see the dot at the top of the graph. You can see here the Climax 50 members that are grouped together. And to see a bit more about the impact of internal variability, we can use a perfect model framework. So here we use the large ensemble, each member as a virtual reference. So we compare each simulation with each simulation from the large ensemble. So it will be the last, each simulation times 50. So you have here a distribution of the weights for each models. So you can see again that they are like the top models show some distribution, which is similar to the one of the Climax 50 members. But you see also several models that have a very small weight, so they will be neglectable if you use that to constrain your ensemble. So intermodal difference here often exceed internal variability, but climatic means we know that it's not. It has a high discriminating power on model performance, but is also not insufficient to constrain regional projections. So we need more than simply climatic means. So if we look at the trends now over that domain, so we have here a trend of about 0.6 degrees per decade in the observation, the red line. And but you see now that estimating that trend from the 50 members gives a lot of uncertainty due to the internal variability, which is larger than the different models. So calculating those weights will also give like some dominating models on the top. If we wouldn't see this ensemble here, we could conclude, okay, that model is the best of the ensemble. We will give more weight to that model, but actually it's quite risky to do that because we know that here there's a lot of noise in the calculation of those weights. So we can see here from the perfect model framework, the uncertainty due to the different initial condition members range total more than the range of the different models. So so while local trends are of high interest to constrain the regional climate change projection, here they provide very low discriminating power on model performance. And now what happened if we combine different metrics? So here I will come back to the metric calculated for the climatic means, also for temperature in winter. So we have the same figure as before. And if we add, for instance, one season, you see that some models survive at the top, but some others are drawn with a much lower value. So if we continue like that, so very few models survive actually at every time that we add a constraint. So we multiply the weights here. So the model needs to be good in every of the 4 metrics. So so there's the exponential function here doesn't forgive. So as soon as you see a bad model, it got drawn in the abyss of the exponential function. So it's interesting to calculate how many models dominate as function of the number of metrics. So here I show the cumulative weight. So starting from the best model, so the highest weight, and after that I accumulate the total weights by adding the model until the worst one. So we see that if we use here only the temperature in winter, you have about 12 models that get nearly 100% of the ensemble total weight. And when we combine the 4 metrics, it's now 1 model that get nearly 100% of the ensemble total weight. So I would not advise to use that to weight regional projections, since the combined weights weights here lead to an overconfidence into one single model, so without any uncertainty. Something that we can do, as was discussed in the previous talk, we could use global constraint on regional projection. So here I just showed some relationship between temperature change for different seasons with the transient climate response of the GCM that is used, or the driving GCM for the RCM. So in green, you have the highest transient climate sensitivity for the GCM, and in pink, you have the 5 lowest TCR. So you see that the relationship is not very strong, but it seems to be there. So green dots tend to be higher than the pink one. So there is some relationship between the global constraint and local projection. So probably new assessment of the global climate sensitivity using CMOS could potentially be used for constraining projections at the regional scale. So in conclusion, we saw that model weighting is highly sensitive to internal variability, and especially for trends. And I didn't show it, but for interannual variability as well. And using too many evaluation metric can lead to overconfidence. So one should carefully choose the metrics to combine according to the application of interest. And in future work, it would be interesting to combine those global and local constraints, and also to define further robust evaluation metric at the regional scale. So thank you very much, and I will be happy to answer the questions.
Thank you, Martin. Any question from the audience? Otherwise, I have one. So you showed that some metrics have such high variability that they're not very useful as metrics for modeled weights. Have you seen in the literature many examples of studies that do use these very uncertain metrics? And do you think that could bias some of these weighted averages that are found?
Mm-hmm. Probably we should look further for that, but it's a very good question. Actually, there are many studies that use also many metrics. There were a few one regarding like a regional climate model ensemble called Ensembles, and they use actually like metric on the circulation, metric on the variability, so a lot of metrics similar to that, and also got to some result of overconfidence. It seems like a problem that not only me found, but it can apply to other ensemble as well. But the problem is when you find a metric that looks good and it reduces uncertainty, and so you try to find a physical relationship between your constraint and the projections, but it's this part that is difficult to be sure that you really use the good metric for that. So here it was just to show that the internal variability can have a really large impact on those metrics, and using this large ensemble was for us like a added value to that subject.
Thank you. So if there are no further questions, I'll thank everyone in the, oh, Nathan Gillett, please go ahead.
Thank you, Martin, for the talk. So my question was, so you saw a very strong dependence of the weights on internal variability. And I think in your first slide, you showed the exponential function used to estimate the weights, and there's a constant there. Can you use a larger constant so you get smaller variations in weights between models? Yeah, so that sigma d I. Yeah, can you change the value of that to get smaller differences?
Yeah, this is a good question, and actually in the literature, there are many ways to estimate that radius of similarity. Some with the iterative methods, But here, I really wanted to give a physical sense to that radius of similarity. So I estimated the sigma t with the internal variability of based on the 15-member ensemble. So so yeah, but if we would define it, for instance, larger than that, like 2 times internal variability or 4 times, you will tend toward like a flat weighting distribution. So at the end, of course the bad model will be less, will have a larger weight, but yeah, is it really what we want? It's difficult to say. Maybe here also the fact that we multiply the weights gives no chance to other models. If, for instance, we would combine the weights of different metric by adding them, here we want a model to be good in everything. But if we would add them, we would like a model to be good in either one or another thing. But after that, it depends really on your application. If you want to obtain weights of general use, maybe adding is a better approach. But for a specific application, maybe it's better to multiply. But I don't know if I answered the question, but thank you.
Thank you. Yes.
And with that, I would like to close the session and thank all the presenters and the audience for your questions, and wish you a nice weekend.
Thank you, everyone.
Can I stop recording?
Oh, yeah.
Sure.